Yeah, this happens when we are working. Okay, we are live.
Okay.
Okay.
Getting.
Yes.
Yes. Like,
Go
should
ahead.
I go now?
Thanks.
Okay. Hello, all. Good evening, good afternoon, and good morning for all participants joining us from different time zones. I am Vivek Rasta, research
Can you
associate
record
at.
this, please?
Hi. Yeah, I'm Vivek Rasta, research associate at Global Institute for Interdisciplinary Studies, and would like to welcome you all to our 5th episode of our webinar series on AI and emerging technologies for sustainable future. Before we begin, I would like to give you a brief introduction of our organization and the webinar series. GIS, Global Institute for Interdisciplinary Studies, is an independent, not-for-profit research-based institute in Kathmandu, Nepal. And yeah, please log on to thegis.org for more info. AI and Emerging Technologies for Sustainable Future is a research group at GIS that aims to conduct research, development, education, and public discourse on emerging technologies such as data science, machine learning, cryptocurrency, cybersecurity, augmented reality, and AI to generate knowledge, innovate, support, and catalyze sustainable development. Over the last webinars, we had guest speakers talking about natural and artificial intelligence, AI and robotics in agriculture, AI in health and medical imaging in optical system, and latest one on biases in algorithms. Without further ado, I would like to welcome our guest speaker today, Dr. Benedetta Dani, who will be talking about development of smart boulders to monitor mass movements via Internet of Things, a step towards a cost-effective early warning system. Dr. Dani is an engineering geologist and geomorphologist focusing on the identification and monitoring of landslides and on the understanding of external controls. She uses cutting-edge technologies for landslide application. In particular, her expertise lies in remote sensing analysis and the use of the wireless sensors. She aims at producing impactful research that has an applicability to society, that can steer stakeholder decision and improve hazard assessment and resilience. She holds a PhD awarded by ETH Zurich, and she's recently a research fellow at the National French Center for Space Studies. Benedetta, welcome you again, and the floor is all yours.
Thank you. Thank you. So I can start now.
Yes, please.
Okay, I will minimize this so you can hopefully see my slides fine. Okay, so first of all, well, thank you very much for inviting me. It's been very nice to be invited, even if it's just on Zoom. I mean, it would be a lot better to be there, but it's better to connect like this than to be forgotten. And I will be talking about the work that we started already in 2019 now. So what do we mean by development of smart boulders to monitor mass movement via the Internet of Things? Well, we have decided to apply a relatively new technology, which is based on the Internet of Things that you may have heard of when it comes to smart homes, for example. So basically, this is having a network of devices that are interconnected and that speak to an antenna, and they don't need human intervention once the network is set up. And the original idea came from Georgina Bennett, who was the principal investigator of the project that I will be talking about today. And the idea is that with this technique, we could potentially think in a future that is not too far. We could think of setting up early warning systems for mass movements with this technology. Why do we bother with landslides? Well, of course, landslides kill people every year globally. And in particular, the Himalayan arc and Southeast Asia are quite susceptible. And I guess this comes from a combination of increasing population pressure on the landscape, susceptibility, the monsoon climate as well, and potentially the fact that maybe engineering of slopes is not so extensive. But even when they don't kill, landslides can cause a lot of problems, particularly to, I would say, developing economies. And this is a slide that I've borrowed from a previous presentation of mine. I have also worked in Bhutan, which is a neighboring country to Nepal, and in a sense, it shares some similar characteristics. And landslides, when they don't kill, because maybe they don't occur in areas that are densely populated, they can occur also in remote regions, they can still, for example, destroy some agricultural land. So this map shows the land cover of Bhutan, and the agriculture occurs on these red specks. So losing agricultural land to landslides is actually a pretty serious issue for economies that are based heavily on agriculture. Also, terrains like that of Bhutan, but also other countries, even countries in Europe, such as Switzerland, and Nepal as well, where we have a lot of relief, make it very difficult to have a dense network, for example, of roads. So having landslides that block roads might mean that lifelines can be really blocked, and sometimes for long periods of time, which might mean that entire part of a country can be without access. So emergency response could become difficult, and delivering of important goods as well. Finally, there is a problem of the growing infrastructure. And I think that in this sense, for example, Bhutan and Nepal are also quite similar, because as I know, in Nepal, you have like an expansion at the moment of, for example, hydropower. And landslide can affect hydropower very heavily, but also hydropower itself can exacerbate existing landslide hazards that are not appropriately identified before construction. So landslides are really something that is important, of course, to study, even when they don't necessarily induce a lot of annual deaths. Although saying that, I don't know what is this number for Nepal. So perhaps somebody in the audience knows. Right. So when we think of the elements in landslide studies, we can look at from different angles. Sometimes we just worry about the hazard, so we ask ourselves questions. Here is just examples about, for example, what is the distribution of landslides? We ask ourselves, what are the factors that control where landslides happen in a certain landscape? We could try to study the level of activity, the displacements that occur in certain landslides, and so on. Of course, we have to take into account the vulnerable elements. And I think this is particularly important in developing countries where there is maybe a period of expansion in terms of infrastructures that maybe is not always matched by an in-depth study of the landscape prior to construction. This happens everywhere, but potentially this is a bigger problem where there is a need for rapid expansion. And then we need to think about prevention. Prevention, we start to worry about it when we do mapping, when we do hazard zonation, and then when we begin to want to monitor particular sites, and when we worry about developing early warning systems. And in this work, in this project, and in the presentation that you're seeing today, we're going to focus on the application of cutting-edge technologies to early warning systems, in particular, this technology of smart sensors connected via the Internet of Things. There are different early warning system types. Just to give you a very basic overview. So I divided them in two categories. We have the in situ monitoring networks to predict failure of particular landslides. And then there are regional early warning systems that often are based on the threshold of a triggering event. In this case, I have the example of rainfall. So the in situ type can be very, very successful because they measure intrinsic parameter of a landslide. But of course, as you can imagine, we cannot plaster very large areas with devices because it's difficult, and you need to know where landslides are already. With the regional systems, we have, of course, the advantage of having a regional overview, and we can kind of have an idea of the hazard assessment over an area, especially in the context of increasingly accurate, for example, weather forecasts. But of course, landslides don't tend to be a recursive event in the sense that they don't always respond to the same trigger in the same way. And sometimes we see new failures where we haven't seen before. And the fact that there is no direct measurement of an intrinsic parameter of the instabilities make them, of course, less accurate. So there are advantages, pros and cons of both types. So the system that we are thinking that could be developed based on the technology we use is, of course, more in the in situ realm. This is just a slide to show what are the overarching aims of the project, which was called the Boulder Project, which is now finished. This was a project funded by NERC, and in the UK, and we had several partners. As you can see here, we were based at the University of East Anglia, but we had also people at the University of Exeter, in other universities in Europe. We had some consultancy company in Nepal as partner, and software engineers and others. So it has involved really a lot of people. And the main idea was to develop a tracking system to observe boulder movement in landslide and floods. Now, why boulders? Because boulders tend to amplify landslide and flood hazards just because of the grain size, which is, of course, increases the destructive power, and also because they are the hardest part of a deposit to be removed. So, for example, in order to have a quicker response, emergency response, for example, boulders can really be a big problem. And the idea is that we wanted to see if this tracking system could become, in the near future, an early warning system in order to increase resilience to landslide and flood hazards. This is just to mention some of the people that worked with me in this project. So we have Georgie Bennett, who is the person who had the idea for this project. Aldina Franco, who was our co-investigator, who is in the realm of ecology, really. And then our technicians at University of East Anglia, who helped substantially in the generation of the network. And then we had a number of formal partners outside the University of East Anglia. And also, as you can see in this picture, we had as well the input of Vivek, who helped us quite a lot in the summer of 2019, where we were trying to solve all the problems to set up our first network in Nepal. There was also a societal aspect of this research, so we tried to really be active in on the engagement side. So we have approached the local authorities in the village of Hindi, where we placed our first network, to get their support and also to inform them of the work we were carrying out. And we also tried to connect to the locals, because they were generally very curious, which was really nice. And again, with the help of Vivek, we had a translation of a document that we could give, because of course it was a barrier with the language there, but we could kind of communicate to them what we were trying to do. And the response was generally quite positive, actually, I have to say. So clearly, even if people are used to this type of hazards in these regions, yes, you could tell that they were seeing us as a positive thing. Okay, so let's go now into the technology. So there are two main components of the network, let's say. So the technology is based on two components. On one hand, we have these sensors, which are, I don't have one here as an example, sadly, but they are actually very small cheap boards. It's what you can see in green here. It's about 2 centimeters times 1 centimeter. It's really thin. It's a cheap board. They are sensors on which other sensors there were other sensors. So there is, for example, a GPS and an accelerometer. We call them smart sensors because of their ability to link to this Internet of Things network, and they're active sensors. So we don't need to interrogate them. They have the ability to send a signal when something happens. And I will describe this more in detail later on. So they are powered by a battery. So of course, there is a question about how long they will last. They have, as I said, a GPS module with some questions about the capability of the antenna. They are equipped with an accelerometer, and we will see that the frequency of acquisition is actually very, very important. And I will explain this a bit more in detail later. They need to have a line of sight, so they need to be visible to an antenna. They need to be protected because, of course, it's an electronic chipboard, so they're not waterproof. So we use resin to embed them inside boulders, and they are very smart in terms of what they can do. So the software that powers them that works on them has evolved to become quite complicated now, which make them very versatile, but also quite difficult to program. And then we have an antenna. So the antenna is actually relatively small. It's about 26 by 25 centimeters, something of this size. If you can see me, I don't know. So it's not very invasive once it's in the landscape. It needs to see the tag. Well, it needs to have some sort of line of sight with the place where the devices are. It needs GSM network, which is not a trivial issue, especially in remote areas. It needs to communicate to a server, and that is why it needs GSM. It needs to be powered, which is also not trivial. in these remote regions. It needs to be protected from lightning and from power surges, which we also found out there was an issue. And it needs a safe place because we don't want anyone to tamper with the antenna. It's a crucial part of the network. So we set it up on the roof of a house in the village of Hindi when we installed the network. So how does this work? So imagine we have a model slope like you have here on the left, and we have the devices that we place inside the boulders. The devices can speak to the satellites, so they can get, in theory, a GPS position, but they also have an accelerometer, so they get some data, and then they send a string of data to an antenna, which is mounted locally, and the antenna then speaks via the GSM network, the mobile network, to a mast nearby, and that's how the signal is then transmitted anywhere we are sitting in the world to a server, and then into our computer, our phone, and in principle, this can happen really within seconds. And so that's why we think that this could be really promising for early warning, because don't forget, and I will say that again and again, that these devices can be activated by movement. So they are active devices. So they can sense something which will activate them. They will collect the data and send it if everything works as it should. Now, when we prepared the network before setting it up, it took us several days to select the sites. So we have to choose not only the boulders in which we will place the devices, but also the geomorphic settings. So for example, in Hindi, we selected a landslide and some debris flow channels. We need to have a safe place for the gateway that also has the visibility to the places in which we put the devices. So you can see that there are some constraints. So this is not something that is impossible to do, but it's something that requires some thinking when installing the network for the first time. Then we need to install the gateway itself. Here you can see it's mounted on a bamboo pole, and we needed to install a solar system to power it in a reliable way. This is inside the house. They were really nice to host our device. And then we need to think about testing and programming the devices, which takes quite a long time. So just to try to simplify things a bit, what these devices used to do when they were active during the season, the monsoon season in 2019, we programmed them to send us one data string every day, like every 24 hours. But we also programmed them to detect movement. So once they detected some sort of movement, that we imposed some threshold, so they could get activated and send the data outside of the regular 24 hours acquisition. The thresholds can be based on either a g-force, so like an acceleration that might be imparted on the boulders, or can be based on kind of an angular threshold. So like if the boulder starts to rotate, then this can also be sensed. So we can have a threshold in terms of the angle or in terms of the force. And then finally, once we're happy with where we want to put the boulders, the devices, when we've chosen the boulders and the sites, when we've programmed our devices, then we need to put them inside. And this requires quite a bit of time. We need to drill and then to emplace them. So you can see here that we put holes in the boulders, and then we emplace the device with the battery inside the hole, and then we top everything with resin, just to protect, to keep it in place and to protect it. We go back to this thing of the thresholds, because we need to select the boulders and then select the setting types and the thresholds accordingly. So I'll try to explain that, hopefully in a clear enough manner. So think about a slope, like in this case. This is just a very, like a sketch of a slope, very simple. Boulders can be either embedded in soil or they can be sitting on the surface. So we selected some boulders that are embedded inside the landslide body. So we recognize a landslide that impinges the settlement of Hindi. And this landslide is made of soil, and there are boulders that are embedded within the soil. They look something like that. So you can see that it's unlikely that they will move in a free manner. They will tend to move with the landslide body because they are really inside the mass. So what do we expect is that these type of boulders will move coherently with the mass as soon as we have a reactivation of the landslide body. And we expect to observe, at least at the beginning, a slow and gradual movement, which can be in the form of a tilt. So look at this sketch here on the left. We have a rupture plane on this idealized landslide, and we have a boulder with our sensors. So the X, Y, and Z are the axes of our accelerometer that are inside the accelerometer inside the boulder. And if the landslide move, then we will observe a rotation, like a variation of the accelerometer values. So the accelerometer senses not only a very large force that might be inputted to it, but it can also sense simply the projection of the gravitational force. So we can see how this projection value changes if we have a slow rotation of the device. And then we selected some boulders that are actually standing on a surface more freely, that can be moved like individually, let's say. So for example, these two boulders lie at the bed, or used to lie at the bed of the debris flow channel that we targeted. And if we had like big debris flows, which I believe didn't occur in 2019, if the intensity of the flow is high enough to pick these boulders up, then these boulders will begin to move and potentially to roll with the flow. So this is what we would expect. In channel, borders are free to move, and so we could expect some more sudden rotations because it's not moving coherently with the mass. So hopefully this distinction is clear. And so these distinctions will really help us to decide how to program our devices on the basis of what we expect to observe. So this is just a recap of our network. We have these sensors inside the boulders equipped with, crucially, an accelerometer, but also a GPS. They can activate as soon as they detect movement, which can be either in the form of tiny angular variation or large forces. And if the network is all connected at that time, then the data is really sent in real time within seconds to the gateway and bounced via GSM network to a server. This, of course, requires that the GSM connection is good at that time, and that the gateway is powered reliably. So here is again the setup of our gateway. And now I will show you a photo taken from this roof. So this is an overview. You can see here on the left, I hope you can see my mouse, there is the gateway on the bamboo stick, and it looks towards the other side of the valley. And here in blue, you have the two debris flow channels that we have selected. One is here and one is here. So they're actually quite far from each other. And here in red is the landslide body that is impinging on the settlement, which is just down here. And the line of sight in this case is between 600 and 700 meters. Actually, this technology can reach much higher distances. That is why it's called long range. It's LoRa one is called the system. But of course, this is in the absence of obstacles. So the rugged terrain really changes that. So it really doesn't allow for such large distances. I mean, it could probably go further than that. So I believe that with the same antenna, the possibility is to monitor more than one geomorphic setting, more than one site, which makes this technique even more powerful than the classic in situ network type. But of course, the connectivity needs to be tested before emplacing the devices. This is how the network used to look like from like in map view. So here is where the antenna is, the gateway from the roof of the house. You can see the Botecosi here at the highway. And here is one of the debris flow channel. Up here is the other channel. And this is our landslide. So we had 23 boulders that we tagged. When I say tagged, I mean we emplaced one of these devices inside of the boulder. Some of them were programmed to detect the small angular variations, typically those that were inside the landslide mass, which we did not expect to move, to tumble down the slope freely. And some were programmed to detect sudden orientation changes and potentially larger impacts, which we didn't see. And I can go into that later, why I think it is. I will show you a couple of examples, this A226 and 9A41. This may be perhaps a little too technical, I don't know, hopefully not. So these are the graphs that I have obtained from the accelerometer. So what are we seeing here? First of all, on the x-axis, we have time. So we put the network in May, and then we observed the evolution, or observed how the devices behaved until, let's say here, October. So for the whole of the monsoon season. And what you see on the right y-axis is the battery. So we can see that A226 had very good voltage throughout, so it lasted a long time. Whereas in October, this other device discharged. So there was some internal variability, and they had quite some important differences, how long they lasted. Anyway, but the important thing is here. So on the left y-axis, we see the actual accelerometer values. Now, the accelerometer in this case was really only recording the projection of the gravitational force. And so this is basically between 0 and 1, depending on the orientation of the axis with respect to the gravitational field. And it is in milli-G, so it's a G force to the -3. Why are they all looking like 0? Because these are not the actual values. I just basically reported everything to an initial position for each axis, only for the purpose of visualization. So what we're looking at here is how the orientation of each axis changed through time. So when you can see that the axis, the yellow, orange, and red, so X, Y, and Z respectively, were around 0 for a long period of time, it means that the device wasn't moving. But then we can see that we have some variation starting at the end of July and at the end of August for these two devices. So something started to occur. Some sort of rotation began to occur. And here, this loop may be stopped. I don't know, but it's just showing like a model boulder. It's not working. I'm not sure why. I will not bother too long if it doesn't start, but it was just to show the small, very like angular change that one of these two boulders might have undergone. It's not working, so no worries. It was just to point out this very small variation that you would never see with the naked eye. But I think it's very important because we're able to capture quickly these small angular variations, which might be indicative of the fact that the landslide is already reactivating. And that was a sketch you've seen before. And then these are the same two graphs, but I will show you something more. So we had also a camera that was taking images every day. And from that, I could estimate in a very rough way. So there was no image correlation technique involved, but just like I picked some features that I could recognize in successive images. And I estimated in the plane of the image, the movement of these features. And I think that I have observed in July and in August, I've seen in some places up to 2 meters of displacement. And this coincides with when we see this variation in the X, Y, and Z axis of the accelerometer. So I think this is not random. It's unlikely that it's just an artifact of our data. So here I have another time lapse, which I hope that you might be able to see. So what we're looking at is the camera images. Sometimes it's very cloudy, so they're dark, but what you will see is that there will be some sliding in this area. We're looking at an angle to the landslide. And yeah, here we had some sliding. I don't know if you could see it. And then later in August, there is another phase. Yeah, now it begins, but then it's even more, yeah, now. I don't know if you could see that. I think it's kind of tricky to see it the first time you see the time lapse, but this is also being put as a supplementary to the paper. So if you're interested, you can actually go through a few times and you will really see the sliding, which again corroborates the fact that our devices are indeed picking something up. I don't know how to remove this bar. I'm sorry. I really don't know. Anyway, so you can't see the titles to the slides, but essentially there are a few things that I would like to point out, so that I think that these devices have shown some small angular changes that are like showing the reactivation of the landslide mass. What we can see also that there is some stagger in the onset of the movement. So if you look at the colors of this boulder, yellow began to move earlier than red, which is the latest onset of the movement. And you can see that there is a first boulder that begins to move at the scarp. Then we have movement in the middle and then movement at the flank. These are only 6 boulders for a large area, but I think that if we had more boulders and more devices in a nice network, denser network across the landslide, we might be able to say something about the kinematic of the landslide as well. What we see also is that in the field in October when I went, I could see some fresh cracks. at the scarps, so in the upper part of the landslide, which are also showing that movement has indeed happened. As I said, the camera images show movement, and we also took some laser scan acquisition, one in April and one in October, and these yellow shaded areas show the movement that is seen with the scan. This is obviously just like it's only two, we can't see really an evolution. It's not a time series. We just have a campaign in April and one in October, but we can see the changes that occurred. And we also see that there is no size dependence. So the boulders on the landslide move irrespective of their size, which is what we expect, because the landslide really picks up anything, any size that is embedded within its body. We go back to the network. This time we will look at some boulders in the channel because they are different. These are 3 graphs for 3 boulders. Now here, I'll show you this loop before it stops. You can see that we have a big rotation this time. Again, this is not in any particular space. It's just to show the entity of their possible rotation that happened for boulder 4C02, which is the first graph, but is not placed at all in the space of the landslide. It's just to show with this change in the values of the accelerometer, what is the entity of the possible rotation. What we see here is that we have very different graphs. So we have, again, 0 values for quite a long time. In this case, actually, we had some change already at the beginning of June, but otherwise we're looking to July and then August. And then we have a sudden change. There is no gradual movement here. It's more of a sudden change. This is because the settings here were very different, because we were hoping to capture high forces, because the boulders were in the channel and we were hoping to detect debris flows. We didn't, and there are several reasons for that. Again, the full explanation is in our paper, but one of the key points is that the resolution, the temporal resolution at which we were acquiring the accelerometer data was only 2 Hertz, so only 2 points per second. And if a boulder starts to tumble, of course, the movement happens very fast. So 2 measurements per second is really not a lot. But also the fact that our gateway was often down because we had problem with powering it in the first season. So sometimes we were only really able to detect the fact that the boulder was in a certain position and then suddenly was in a much different orientation, but we don't really capture the movement as it unfolds. So this was a downside of our first acquisition campaign. Anyway, here are definitely points where something has changed. And the key points are that some of these boulders I couldn't find anymore in the debris flow channel when I went back in October, which means that indeed they moved. Again, we have field camera and scan data that show movement in the channel. And this time there is size dependence. And this is actually also a kind of a clue to the fact that there is some reality in this data, because we didn't have some very big debris flows in 2019. I think last year was worse. And so we couldn't expect large boulders to be picked up by the flow as the smaller boulders. Only the small boulders appear to have some data in the accelerometer that is compatible with movement. So this gives us some extra confidence that we are looking at something real. And the data is often sent in real or near real time, except for the times where, unfortunately, the gateway was not connected, either because of GSM failure or because of power failure. This is just, again, the qualitative, very qualitative validation. So here you can see what I did. So this is one image from the time-lapse camera that is looking at the side, the landslide. And you can see in the circles, they are features that I visually could recognize, either a boulder or a bush or a tree. And then I could track them in successive images day by day. And so these lines are actually the vectors in the plane of the image that show an estimate of the displacement. And this is a scan data. So this is now looking at the landslide from, like, we're looking at the scarp, basically facing the landslide, only in the upper part. And here, if you can see the circles, the gray, yellow, and red circles, they are some of the boulders that had devices inside them. And what you can see is that we have a lot of blue and red patches in this region. There are also a lot of holes because there is a lot of vegetation, which impairs the visibility with this laser scan. But you can see that something indeed has happened. And again, some of these boulders I was unable to find because they were covered by material that came down from the upper part of the landslide. And for the debris flow channel, we can actually see this is 4th of June to 5th of June, and you can see some boulders dropping from the side bank into the channel. Again, we didn't see any important debris flows, but there was definitely some boulder movement in days in which we had intense rainfall. And again, the scan data looking into the channel from the sides shows that there are plenty of areas of erosion in blue and accumulation in red. And again, the crosses show the boulders that I couldn't find anymore. So this is just to show that it's unlikely that the data we obtain with the accelerometer is purely an artifact. I think that there is reality in there. Challenges, we encountered many, really very many. And that is in a way why this pilot study was so important, because we have already thought of ways to overcome many of them. And I can just give you a little overview. So first of all, we are sitting up here. This is a map of the GSM coverage of Nepal. You can see Kathmandu here, and this is our study area. And blue is good coverage and black is not so good coverage. And yeah, I know that there was one mast up there, but I also thought I heard that they were developing the network, so they were adding antennas. At the time, the GSM network was somewhat sporadic. So there were times in which our gateway couldn't be connected because simply there was no signal. So this is a problem we cannot obviously do something about ourselves, but in the future, I think that this will become better and better because there will be development in the network. Powering the gateway in a reliable way was a big issue. So we fried our first antenna. Vivek might remember that drama, because initially we thought that it would be enough to power it into the main supply of the house. But actually, as you might know, in that region, there are quite a lot of power cuts. It's a daily occurrence. And when the power comes back, then the risk is that there is a power surge. So we fried our first gateway with a power surge. So then we rushed in a solar system, but the solar system at the time wasn't that reliable. So our gateway, if you see here, for example, in May was connected only 10 days, in June was connected only 13 days, July only, 13 and something days. So as you can see, we had a lot of downtime. In October, I went there and with the help of one of our technicians, I rewired the whole system, and now we have a very nice system. Most parts can be sourced locally even, and it's not that expensive actually. And our gateway has now been powered pretty much constantly, except that of course, we were unable to put more devices. So it's there waiting for us to be able to come and put another batch of devices, I hope next year. Now, we got some of the settings wrong. So we had some angular thresholds that were set too low, but maybe this is a bit too technical, but basically what happened was that some devices start to collect a lot of spurious acquisitions, which you can see here. This is the number of acquisition per day. Anyway, it's just to say that we had made some mistakes, which we are now aware of. And the fact that you have a lot of spurious acquisitions, you increase the noise of the data. This is not a big deal because you can clean the data after, but of course you decrease the battery lifetime. The poor GSM performance was a problem, and I can tell you why. So here on this graph, you see all the sensors. So every bar is one of our 23 sensors. And you can see the success rate as a percentage. What does that mean? So every time that the sensor is trying to take an acquisition, either triggered by movement or a regular acquisition, it will try immediately. It was trying immediately to get a GPS position as a first thing. Often because the valley is very narrow, there is not a large number of satellites visible to the sensors. So we see that the GPS really struggled to get a position. So the success rate of, for example, here for this sensor 3 here is about 20%, means that 20% of the time it managed to get a position and 80% of the time it failed. And because we set a threshold, like a time threshold, we left the device 3 minutes to look for the GPS before it would abort and say, I can't get a position. This meant, unfortunately, that the accelerometer was waiting to be able to record the data until the GPS tried and tried and tried and then eventually failed. So it created a lag in our accelerometer because at the time, the two sensors, the GPS and the accelerometer, were tied together. So of course you can imagine that if the boulder begins to move, the device activates, but then it starts to struggle to get the GPS and it might take 1, 2, 3 minutes. The boulder movement might unfold within seconds. And if the accelerometer can't record that, even if there had been, let's say, a large impact force, you won't see it because it's not recording in that time. So this is something we had to change in the way the sensors work. And we also try to think of ways to embed the devices in the boulders in a manner that we can then retrieve them and use them again. So we were, as I told you, we used to put them directly inside the resin, inside the hole. But like that, the devices that are now there, they got discharged because they've been there since 2019. They're not working anymore. The battery isn't going anywhere because the epoxy resin is super hard, but we cannot retrieve them. So they're gone, they're wasted. So since then, we thought about more rudimentary ways, like you can see in this middle figure, and like neater ways that we are exploring now to encase the device and the battery in a way that we can slide a tube inside the hole, put the resin just on top. And when the battery is discharged, we can just melt that little layer of resin and retrieve it, change the battery and reuse the tag. And this will be very important because when you buy a bunch of tags to monitor a few sites, you don't want to waste that money. A tag is about 200 pounds. So if you buy several, of course, the money adds up. But if you can reuse it, then this will become a lot more cost effective in time. So just to summarize the future developments, we have now learned more about the settings to program the device for the next installation, which we hope should be next year. We can now think of retrieving our tags and reuse them again and again. So potentially even then have people locally the next time around to go there and just change the batteries and reinstall them. We have separated the accelerometer from the GPS. And this is crucial because it means that now the accelerometer will be able to activate immediately as the movement begins and send this data in real time without waiting long minutes before the GPS is acquired. And this is crucial for the early warning system. We've increased the ability so the frequency of the accelerometer. So before it was only 2 hertz, 2 acquisition per second, which is really not a lot. And now we can go up to 50 or 100 hertz, which will really help to see the movement as it unfolds and to potentially capture larger forces, which will be important to tell us something about the intensity of potential debris flows, for example. We reconfigured the solar system, so now the gateway is powered much more reliably. We are looking at activating other sensors that are present on the board and that were not active in 2019. Although I think the most important part of future research in this area will be understanding how do we set the threshold in order to have an alarm sent. So at the moment, we didn't think much about that because we will need many more sites to be monitored in order to really understand what are the ideal settings or the ideal thresholds in order to have a message sent that will alert us of something hazardous happening. So this is just the conclusive slide to summarize. We had 10 out of 23 boulders that we tagged in 2019 that show patterns that we believe are compatible with movements. 6 of them were in the landslide and they show just the reactivation of the landslide, and 5 of them were showing movement within the debris flow channels. And we think that this data is promising and showing that this technology can be used in a not too far future for early warnings, even if it's not yet ready. But we have already thought about many improvements that hopefully will give us better data for the next season. And we do think that this type of monitoring can become more and more cost effective and will be possible to upscale it and to apply it to other sites in the future. So I will conclude here. If you're interested, this paper is out. It's been now online for a while, but it's now fully published. This has been made a highlight article on Earth surface dynamics. And I think that potentially this is because it's really the first time, as far as we know, that this Internet of Things and this smart sensor technology has been applied to a real field setup in the geomorphological realm. So I will stop here. And if you have any questions?
Yeah, it was really a very informative. Yeah, am I audible?
Yeah, okay. Yeah, you are.
So yeah, it was very interesting and insightful study. So I think we can start open our floor for the questions. So we already have questions actually. So Basantaji, would you like to ask question yourself?
Yeah, thank you, Dr. Dani. This is Basanta Adhikari from Institute of Engineering, Tuban University. Very wonderful presentation, and I have gone through your papers also little bit.
Thanks.
I was there in your site in 2019 with Christine Christophs and others in ESU Galileo meeting. So I have two particular questions. As you said that this technology is evolving, you can set up or develop different kind or modify the different technologies or the technical things later on. But the important thing is that when you install this system in a boulder, in the landslide, generally in the Himalayas, the landslide has a different zone. And if you consider the rotational failure, then it has a different zone, and the boulder are lying on the top and side and the bottom and the middle. And then in terms of identification of threshold in the Himalayas, I mean, how do you plan to do on that, a calculating threshold to reduce the false alarm, the first one. And the second one is people in Nepal, as being a Nepalese, we have to rely on the low-cost technology for the sustainability, for research, modeling, scientific papers. We can use high, broadband seismometer or something like that, what you have actually installed. But for the people, for the sustainability, we need low-cost technology, which community can operate later on. So do you have anything on this regard, comments?
Right, okay, yes, thank you. So I guess it's more about the cost effectiveness of the technology, right? The second question.
Yeah.
Yeah, I think that actually when you think in terms of other, it's not cheap in an absolute sense, right? So as I told you that, maybe I didn't, the gateway itself is about £1,200. And then you have the cost of the devices, which is about £200. I think what really is expensive for the device itself is the software development that makes them work. So this cost will come down in time because a lot of this development has already occurred and is occurring as part of research projects. So we have a follow-up project in which this development is ongoing still. So the potential is clearly there in the future for this technology to become cheaper, because once we have our software developed, then the cost might come down, particularly if the devices are bought in bulk. But when you think about, so the network itself was not super cheap this time around, but when you think, for example, at monitoring a slope with a different method, for instance, ground-based INSAR, this is a lot more expensive. And it's a lot more expensive, not only in terms of what you need, like the devices, the machine you need, the technology, but also the processing, time of processing, the expertise that is needed, and so on. So I think that in this way, and plus, when you think about other in-situ monitoring systems, which are also often quite costly, or that requires drilling of holes and so on, like maybe boreholes. Again, with this technology, you have one antenna, and with one antenna, you might be able to monitor several places. So of course, this also makes it more cost effective. Like in this time around, we only had 30 devices that we wanted to spend for the pilot study because we knew that some things could go wrong. But if you have many more devices, then you can have more than just 3 sites with one antenna. So this makes it, I think, in the future will make it more cost effective than other technologies that are currently available. Now, the problem of the threshold is still a problem that, I think it's what we are still quite far. As I say, we have another study now, another project, I should say, quite big actually, that is led by Georgina Bennett, who was also leader of the Boulder Project. And in this context, there will be many more sites that will be monitored, from debris flow channels to woody dams. So in the UK, there is this tendency now to introduce woods in order to dam rivers to prevent large events, prevent flooding. And so the idea is that now many more sites will be monitored and more data will be analyzed. And hopefully this will help understanding how can we really manage the threshold issue. The other thing is that probably we will need to do, I don't know, might need a need for some modeling and also to associate our devices with other type of technologies that might help to really validate better in a more quantitative way rather than qualitative, in order to be able to detect, to understand what are these thresholds. But this is what we still need to think a lot more about.
Thank you.
Yeah, we have next question from Jacob. Jacob, would you like to ask a question yourself, please?
Yeah, sure. Thank you very much. Thanks for the great presentation. I'm a PhD student at Utrecht University, and I live in Kathmandu now, and we work a little bit further to the west in Rasuva. We also have these, so we're more interested in hydrology, but then also hydrology for landslides and for hazards. And we have these smart sensors, very simple stations standing around that are also connected to the GSM network. And I think some of that you answered along the talk then, but I was just wondering how much battery you're using for this connection to the GSM network, because that's a big issue that we have, is that a lot of our battery is drained by trying to get connected to the GSM network. First, I was expecting we would need a lot more energy for the sensors itself, but that was never an issue. So the sensors are collecting data fine, but to get it actually up, because it's drying all the time, right? And then there are issues with the network, so it's turning on and off, and it keeps drying.
I see. Yes, this is because so your devices are directly speaking to the GSM network.
No, yeah, so we have devices, they are connected to a data logger, and the data logger speaks to the GSM network.
Right, okay.
We can control that, how often it does that.
Okay.
Right? So in the beginning we said, okay, talk to the network every hour. Then we said, no, talk to it every 4 hours. And then at one point, and in some locations, we had to adjust it to every 3 days. But we had to manually trial and error, fiddle around until we realized, because we don't have huge batteries with these stations. We could, of course, put a bigger battery, but we want to keep we have a solar panel as well. They're rechargeable, but we want to keep it small. So we don't want to have a huge battery. So yeah.
So I think it's slightly different the way the networks are set up, if I understand. So our biggest problem in terms of battery expenditure was the GPS, because the devices themselves were trying to collect the GPS. But actually, so this is what really drained I think is what drained the battery of our devices. But the connection, which happens via the long range, is not very expensive at all. So I don't know how do I didn't quite understand how your devices speak to the logger, but our devices speak to the antenna via the long range, and this is actually not expensive. So the worst was the GPS, which we'll now plan to deactivate for the next time around, because we really don't need it. And then the GSM connection only happens between the antenna and, from the antenna to the server, if you see what I mean. So once the antenna is powered reliably and is powered with 2 big car batteries by a solar system, this is really not a problem anymore for us. But yeah, I think we also had to do a lot of trial and error. And also the other thing that we discovered was that there was a huge variability between devices, and it's, not always sure why that's the case.
We have one more question.
Yeah.
Krishna ji, would you like to ask yourself, please?
Thank you very much for your nice presentation. I listened it in detail. My question is, you talked a lot about the battery and then this and that. For that, who is the responsible agency to handle such system after installation at site? Number one. Number two, if that is the local government, then have you trained local government, let's say technical person, maybe engineer or whoever else there? or it is directly related to the our federal government, Department of Hydrology and Meteorology, or other? Who is your, the partner to work and to implement this kind of activities in Nepal? Government agencies. I'm not asking about the private or other companies.
Yeah, so at the moment, this was really just this is a great thing to think about, actually, because it will become more important in the future. If, of course, there will be the interest to upscale such type of networks. Because at the moment, it was really managed by ourselves. So we simply got in touch with the local authorities to say, hey, this is what you're planning to do. Are you happy with that? And they gave us that letter. And that was it. But ideally, and we have tried to do some workshops in Nepal via the partner we had at the time for this project, which was Scott Wilson Nepal. And the idea is to try to get some other agencies on board, like, I don't know, as you say, Department of Hydrology or Road Department. Because ideally, it would be great if, the engagement in the future could become even stronger, and it's not just us telling some people what we've been doing, but potentially empowering people there to manage the networks. And as I mentioned during the talk, potentially getting somebody that wants to, be in charge of that and go check when there are problems with the gateway or replace the batteries when they are discharged. I think this is something that needs to be explored in the future, and it would be great if there were agencies that were willing to collaborate on that, because then we can really, pass on kind of some of the knowledge we have, and then we would have people managing the network, especially when we can't travel. So
okay. The ownership by the government agencies is the most important thing for the sustainability of this kind of early warning system in Nepal. I'm not only in Nepal, throughout the world, So that's why I'm raising this question, whether the government agencies are involved or not. And your idea to engage the government agencies, at least local government, and train them, and then the agencies like you just mentioned, Scott Wilson or some other agencies involvement could be good. But without giving the proper training to the local government, and without their engagement and the sustainability of this kind of early warning system is always questioned. That's why.
Yes, of course. Yeah, no, of course. So as I say, it's not always easy to keep this kind of relationship going at such a distance. But but we have tried to make an effort in this respect. And yes, Scott Wilson Nepal was actually quite helpful, because they tried to get on board as many people as possible. And we did raise, we had some interest, but I think there is more to be done as well in not only from the technical point of view and the research point of view, but also on that side, so that we really get a clear channel so that this can happen in the future. But thank you. Yeah, this is really a good point.
Yeah, do we have any more questions? We still have some time for that.
Can I ask one question?
Yes, Damdai, please.
Thank you, Vinny, for a very interesting presentation. And I'm very excited about the future of this technology. My question is regarding the cost effectiveness of this kind of technology. In the wildlife field, what I have heard and seen was that they use this motion tagging sensor, and that is very kind of low cost, like $10 or something like that. So, but you mentioned it costs around £200. So do you think, in the long run, since this project, I assume, is a pilot project and you are testing whether this technology works or not. So do you think in the future, because it has a huge potential in developing countries like Nepal or landslide prone countries. So do you think in the future, the cost of this technology will go down and then it is widely usable?
Accessible. Yeah, I think so. As I said, I think what we're really paying quite a bit is the help in the development of the software that activates these tags. So there's no doubt that this will become a bit more accessible. Now, I can't really quantify, what will the price be in what period of time, but we're really kind of patenting almost these devices at UEA with another partner company in Zurich, in Switzerland. And really the cost comes from the time that is involved in developing the software to do what we want them to do, if you see what I mean. So surely this will be less expensive in the future, but I can't quite quantify now. But I don't know what motion sensors we're talking about, but our sensors have really the special feature of being activated by movement and being able to send a signal without being interrogated. So we don't always only have the capability to look at data back in time, like retrospectively, but they can be activated. So this is really the plus side of this technology.
Yeah, thank you, Benny. So I think we'll take a last question. So Basan, you want to ask another small question? So then we can, wrap the session.
Dini, just wanted to know more detail about, because you told that Georgia Bennett is working on the large project in the English or Scottish Highland to understand or to develop the threshold. But Himalayas is quite different. You cannot really put this threshold over here. So how can you import this kind of threshold things over here? Just wanted to know more about it. Thank you.
But again, I think that this will really only come with more experience of testing the same areas and to have more kind of a bigger pool of similar geomorphic settings. So more landslides and more debris flow channels. I mean, with one season of acquisition, we can't really, there was no way that we would ever be able to have thresholds on there, for example, angular variation to detect when the landslide would start to become, to hit a hazardous level of activity. I really think that this will only come with time. So if we can deploy more devices with time and observe more and more of these processes, we will really understand better where we're going to head with that. Of course, I mean, testing in woody dams doesn't give you the information that you will need to test devices or to have devices deployed in a debris flow channel. But as soon as we learn more about these devices, I think it will become, it will still be a positive experience, if you see what I mean, as we observe more and more. I don't think that there is a straight answer. I think that we'll need to test.
Thank you.
Yeah. So Dovan Didi has one last question. Dovan Didi, would you like to ask?
Okay. Thanks again, Dr. Dini, for such an amazing presentation. It was very intuitive. So my question is, because you had mentioned one of the big chunk of the cost goes for the development of the software. So I was assuming maybe now different labs are creating their own software, but once this technology moves from research labs to more into application and industry, maybe there could be some standardized software, that can be, copied or replicated or scaled up. So do you think in that stage, the cost of software will not be that monumental, or am I missing something?
No, I actually don't have full visibility on this aspect of things. I think that this is very much related also. For example, we selected a partner, right? We selected this software engineer because we already had a collaboration ongoing via one of our co-investigators. So that software is kind of a commercial software in a way, the way that this company sees it. So we pay for that level of expertise, right? But then I don't think that that particular software will be easily transferable. I mean, I think that this has been generated by this company and we get it from them. What I meant by the fact that the cost will come down is that now we're paying for all this development. So when we are happy with how this software has been developed, I think that when we go and buy more devices from them, they will become less expensive. When it comes to developing their own software, I mean, I don't think that this is possible. There will be other people, of course, that can develop software for devices of this kind. But yes, I think that, as I say, this is a commercial company, so it will not be directly transferable. And every time that we begin something from scratch, of course, there is a lot of work to be input. So I can see that from our side, we're likely to continue to use the same developers. But yes, I mean, this technology, once the concept is proven, that doesn't stop anybody else from maybe using something similar and developing their own software. But yeah, I think this is not, I mean, you need an expertise to do that.
Yeah, I would like to add another comment, more comment and question. So when you mentioned that this the companies who are producing this hardware, who are also producing software for their hardware, so that's why they have let's say monopoly, or they have the inside information that they are the only one who are developing it. So in some ways, it kind of, I'm reminded of all the vaccine, intellectual property debate going on right now. So I was wondering, if there could be some very collective voice, because again, this is such an amazing technology, and for not only for human and community, but for the the climate and everything. So if there could be some collective initiative to make those the software more accessible. Yeah, because once, yeah, maybe if you are only selling 5 units, right, you need to have that high thing. But if you are selling 500 units, there's no reason you should have the high margin, right? So as long as they have this very reasonable profit margin, I mean, again, paying a lot for the software doesn't really make sense. So yeah, I'm just all this vaccine debate.
No, you're completely right, and I don't know where this will go in the future. I also don't know how this collaboration will continue with Andreas Sen, who is actually one of the co-author of the paper. You can see him named there, so you want to look him up. But don't forget that really, yes, you're right. There are a lot of software that are actually quite expensive, even once they are fully developed. But what we're doing now is asking a lot of a software engineering time to really make this from scratch. So I don't know whether this will ever become very cheap, but we are in a phase in which we're really making this, at least ourselves, for the first time, and therefore there's got to be the cost of this time, if you see what I mean. I mean, the time invested in this actually being substantial. So that's why I can only foresee that this will decrease, but yes, I don't know whether this will ever be something that will be freely available. I suspect potentially, no, not with a company like that, but yes, I can't quite foresee where this will go.
Thank you.
Yeah, thank you, Rowan Didi, for the questions. Thank you, Bene, so much for your time.
No, thank you.
We really had engaging time. We really learned a lot, and I really see potential of this kind of technology. As you can already see, we have been thinking of sustainability, how the things could be reused, which wasn't there before. So I really wish good luck with the project and upcoming endeavors. And we can see how this interdisciplinary research, the tags that are used for the tracking animals, is now coming to the geology and geomorphology. So there's a lot of potential on this kind of research as well. So I think with that, I would like to thank you so much for giving your time.
Thank you.
And yeah, we really loved having learned so much about you, and we love to collaborate with you in the future. So
yeah, this would be great.
So much.
Thank you very much.
We'll see you in Nepal very soon.
Yes,
okay.
Hopefully.
Thank you.
Thank you so much, everyone.
Yeah.
Thank you.
Bye-bye.
Thank you.
Bye. Bye.
Bye. Ciao.
Bye.
हामी बस्नु के छ
हजुर उत्तम दाइ को छ भने लागि यहाँ
ए लाइभ अफ गर्नु पर्यो
हामी त्यो चीजको मात्रै छौं भने बसौं र के छ भने गरौँ है
लाइभ अफ गर्नु पर्यो
लाइभ अफ